Last time, we defined the magnetic flux density B and wrote down all four Maxwell equations in their static form. But the question stayed open. What does B actually do? Today we answer it. B exerts forces on moving charges, torques on current loops, and it magnetizes materials. By the end of the video, we'll have the force and materials toolbox we need to handle motors, inductors, and magnetic recording. Start with a single point charge Q, moving with velocity v, inside a magnetic field B. The force on it is given by the Lorentz law, F equals Q times V cross B. Why a cross product, not a simple product? Because the force is always perpendicular to both V and B. If the charge moves along B, V and B are parallel, the cross product is zero and no force acts. If V is perpendicular to B, we get the maximum magnitude QVB. The direction follows the right-hand rule, just like in Biot-Savart. One important consequence: since F is always perpendicular to V, the magnetic force never does work on the charge. It changes the direction, not the speed. That's why charges in a uniform B field move in circles. If we combine electric and magnetic forces, we get the complete Lorentz force. F equals QE plus QV cross B. The electric part accelerates, the magnetic part curves. Now scale this up to a current-carrying wire. A current I is just a bunch of charges moving together. For a tiny piece of wire DL carrying current I, the charges inside give rise to a force. Using dq times V equals I times dl, the Lorentz law becomes dF equals IdL cross B. Integrate along the wire and we get the total force. F equals the integral of IdL cross B. For a straight piece of wire of length L in a uniform field, this simplifies to F equals IL cross B. Magnitude is ILB sine theta, where theta is the angle between the wire and B. This is the formula behind every electric motor. A current-carrying coil inside a magnet feels a force, and if the geometry is right, that force turns it. What about a closed current loop in a uniform field? Here, the net force is zero. The forces on opposite sides cancel. But there is a torque, and it tries to rotate the loop. We define the magnetic dipole moment m as I times A times n hat, where A is the area of the loop and n hat is the unit normal chosen by the right-hand rule along the current direction. Why this particular definition? Because with it, the torque on the loop in a uniform B field takes a clean form. Tau equals m cross B. Same structure as the force law, just with m instead of QV. The cross product tells us where the loop wants to settle. If m is parallel to B, the torque is zero and the loop is at rest. If m is perpendicular to B, the torque is maximum and the loop rotates to a line. Exactly like a compass needle settling in the Earth's field. The associated potential energy is U equals minus m dotted with B, minimum when aligned, maximum when anti-aligned. So far, we've put currents and loops inside an external field. What happens when the field is inside a material? Every atom has electrons orbiting and spinning, so every atom is a tiny current loop with its own magnetic moment. Usually these point in random directions and cancel out, but in a field B, they partially align, and the sum per unit volume is called the magnetization M. With M around, the relationship B equals mu0 times H picks up a new piece. B equals mu0 times the quantity H plus M. And for linear isotropic materials, M is proportional to H. M equals chi mH, where chi m is the magnetic susceptibility. Plug this in and you get B equals mu0 times 1 plus chi m times H, which we write compactly as B equals mu H, with mu r equals 1 plus chi m being the relative permeability. Materials fall into three classes. Diamagnetic, μr slightly less than 1, weak opposition to B, like bismuth or copper. Paramagnetic, μr slightly greater than 1, weak alignment with B, like aluminum or oxygen. Ferromagnetic, μr much greater than 1, strong alignment, like iron with μr around 2000, or permalloy with μr up to 100,000. These are the materials that make transformers, motors, and hard drives possible. Quick wrap. The Lorentz law, F equals QE plus QV cross B, is the single equation that governs how fields push on charges. Scaled up to a wire, we get dF equals I dl cross B. For a current loop, the torque is tau equals m cross B, where m equals I a n hat. Inside materials, the field couples with atomic magnetic moments through the magnetization M, and the relative permeability, μr, classifies materials into diamagnetic, paramagnetic, or ferromagnetic. Next video closes the static block, magnetic boundary conditions between materials, inductance, and magnetic energy storage.